Here we have the scope set at 5 volts per division for the inside signal, and we have the scope set at 100 volts per division for the outside signal. Here we can plainly see, hopefully, that the inside field as the primary, that shows the expansion and the collapse of the field, the primary field. We'll turn that back up. We'll turn the secondary back up to 5x times 10x probe setting. We have one of these coils in between the primary and secondary. That coil is giving us that signal. We'll show that on the apparatus shortly. Okay, we can probably see a little plainer there. That sweep rate is at 10 milliseconds per division, given 100 milliseconds in a complete sweep, and the camera only records 30 frames per second. So that's why you're seeing that time lag with no visuals on that scoping. It's hard for this camera to record low sweep phenomena, but we need that low sweep phenomena in order to be able to show here exactly almost 5 cycles at that point there where it goes to 0. You still have 150 volts on the secondary. It takes it a full 5 cycles before it goes down to its lowest point of 125 volts. Okay, having said all that with the scoping, we'll go on. We have elevated secondaries. These secondaries should be able to see a white checker and a sensor coil placed in between the high induction coils. We're monitoring the second coil in the phase rotation. Now we have a problem here. Each of these are 2.6 Henry and 2.7 Henry. So we go over here and we looked at our increased better results. Formerly we had about 300 volts when the inductors were straight on the poles. Now we got about 328, 329. We got 206 to 8 volts on the front coil, and we got 149 on the coil that we're monitoring. Of course, you have to realize that since that secondary voltage is varying, that meter is only taking the average of that variation that it sees. Okay, the problem that we had before is that if we we also got amperage meter on the front coil. It's showing a fluctuation in the vicinity of 30 milliamps. Of course, you know, we have the reason that this thing is appearing so cyclic is that it's moving up and down every 24 cycles. So we're going to call that 30 milliamps. And then we got 207 volts. And then we got a reading we got a division there telling us that 208 volts divided by the 30 milliamps gives us a 7,000 ohm reactance. That's all good and fine. That should be what the LCR meter predicts at 2.6 Henry. Now we go over to the next 149 volts. Excuse us. We got 448 volts, and we got, we'll call that 39 milliamps in the circuit. At 148 volts, we'll do our subtraction. .0388. That's what it's reading. So now the division's telling us on that information on the back coil. What's wrong with the focus? Don't seem to be getting the focus here. That information is telling us we only got 3,800 ohms reactance on that side. Since we got more reactance on one side than the other, well, that explains why we got more current. 39 milliamps. This was the problem. We couldn't understand what's going on with that figure. So what we're going to do now, repeat what I formerly did earlier today. We're going to disconnect the left meter, give it a short. And that should be showing us back to our former condition. The 149, 208. We'll move that metering. And 330 volts in between there. Now I'm going to walk in front of the camera and disable this amperage meter and make it a short. Now we should have the same circumstances again. We got 207 at the front coil, 148 in the back coil, and 330 volts in between us. Now I'm going to go in there and take the meter and read just the 150 volt side. I was formerly at 38 milliamps. I'm going to disable the cap side. Connect the meter read. Now we see we got this meter telling us it's 23 milliamps. Just put 148 divided by 23 milliamps. And that gives us more of a correct answer. 6,400 ohms. So that solves that riddle. Apparently, problems are brought in by taking two simultaneous amperage readings. Now that we see that's been resolved, we want to look at the influences before. I don't have my notes here. I want to get my notes for this. These are some notes taken from a previous video where the inductors were straight over the poles. And at that time I concluded, since we had the low ohmic resistance on the second vector pointing straight up, that it would be inductively lagging. And sure enough, when we measure these voltages, 150 and 207 with 330 between them, we find it's about through 135 degrees instead of 120. So that's probably what's going on in that case. The 1 meter's appearing to be a little bit lagging, and in finality then, when we reverse the phase rotation by reversing the coils in that video, we found that we had a much lower voltage, 188, just by reversing the coils. But when we reverse the coils, that's the same thing as reversing the phase rotation, and this arrow now went left, making that a smaller angle, where in the first example it went right, making it a larger phase angle. Now we're going to try to quickly show what's going on with some of these. We also had problems with formulating what our Q factors were. What we can do here is, if I can remember, we're going to disable the capacity on the right side, leaving only a reactive current. Now we have a reactive current noted at 19 volts. Reactive voltage, pardon me. The 19 volts, 150 divided by 19 will be the Q factor for that coil. Note that the 19 and the 172 sum to 156. Okay, now we're going to repeat that. On the other side, we're going to just disable the other side also. Now what happened when we disabled the other side? Now we got 18 reactive voltage in the front, and we got 22 reactive voltage in the back. So now then we'll re-hook up back voltage. Note that it's 160. We re-hook up the front voltage. And note that when we do this, this will go down. Right down to 150. I hope the camera's catching that. So we could say in one case it'll go down, and in another case it goes up. And according to another, probably a factor of the phase rotation. So then we demonstrated that correctly. We want to show that when we take out this one, take out the front, cause that one to rise. Take out the back one, cause the front one to go down. So those are the interrelationships. I'm trying to solve this puzzle. And we're probably ready to call that quits. And take a note at our scoping again, which may be problematic for the viewers. Let's see if that's turned down to a low level. That may be a better accessible view. You cannot tell on the camera. And we'll close out here by noting that we have the whole system elevated on glass jars so that we can do further work with monitoring the field coming from the bottom of this assembly. So for now, we will call this video quits. Thank you.